Hello friends, welcome to Physics Online. I am Sudhir Vaidya and today we are looking at photoelectric effect. So in metals there are free electrons, we all know, that is why they conduct heat and electricity. These free electrons move in a random fashion, not along any path or with any fixed velocities within the metal. Now if you have to remove one of the electrons, in order to remove the electrons from the metal, we would need to expend energy, or in simple words, we would need to do some work. Now, the energy could be provided in many ways by having a very high electrical field of the order of 10 raised to 3 or 10 raised to 8 voltmeters, which could pull out these electrons. This process is called field emission. Another method is very simple, we just heat the metal, thereby the electrons acquire the requisite energy and they come out of the metal. This process is called thermionic emission and this is quite often used. Another method is basically we do this for getting X-rays. We use fast moving electrons and we use these fast moving electrons to strike the metal. As the fast moving electrons enter the metal, they collide with the electrons inside the metal. As a result, the energy of the moving electrons is transferred to the free electrons and they get the energy required to come out of the metal. This basically is called secondary emission. One of the interesting way to provide energy to the electrons is to have light of suitable frequency. Remember the word suitable frequency because that will be of very importance to you as we go along. So this light of suitable frequency falls on the metal. This phenomena whereby we can remove electrons from the metal by simply making light fall on the metal is called photoelectric effect, and that's what we are going to discuss today. Anyway, all said and done, the minimum amount of energy required by an electron to just escape the metal surface is called work function of the metal. Now, this work function is typical for a metal, that is every metal will have its own work function. This is normally denoted in most books by W0 or psi 0. Since this value is very small, we measure it in a unit called as electron volt. So let's see what is electron volt. So as you can see, if an electron goes from a lower voltage to a higher voltage, or it moves across a potential difference V, then of course it acquires electrostatic energy, and this energy manifests itself, and or rather we can see this energy by the time of increase in velocity of the electron or in the kinetic energy of the electron. So now we define electron volt, that is the 1 electron volt is the kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt. So accordingly 1 electron volt will turn out to be 1.602 into 10 raised to minus C coulomb into 1 volt, and ultimately we have 1 electron volt is 1.602 into 10 raised to minus 19 joule. Now mind you, this is given in the shaded portion, is a very important thing in all part of the chapters which you are going to do henceforth, like atoms, nuclei, and semiconductors, etc. Here are listed some of the metals and their respective electron volts. So some have high some have high work function, some have less work function. So we have just listed them. It's just for you to peruse and just see them. So now what is photoelectric effect? Now as we have seen, when light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. This phenomena is called photoelectric effect. Now, photoelectric effect incidentally was discovered by Heinrich Hertz in 1887. He was actually demonstrating an experiment to demonstrate existence of electromagnetic waves. He found that high voltage sparks pass through the metal electrodes of the detector more easily when cathodes are illuminated by ultraviolet light. The ultraviolet light falling on the metals caused the emission of negatively charged particles. At that point, we had not given any name for this negatively charged particles. Today, we all know that they are electrons. Another possible phenomena was investigated by Hallbox and Phillips Lenard, that is demonstrated here. So we take a metal and we connect it to a electroscope. So as soon as ultraviolet lights are incident on the SiC plate, the two leaves of the electrode move away, which shows that they both acquire negative charge. Now we are ready to examine this phenomena for ourselves. So over here we have an experimental setup for studying photoelectric effect. We have taken an evacuated tube over here, and inside it we have got two plates. One is a photosensitive metal plate, so that when the light falls on it, electrons will be emitted. Then there is another plate which is possibly going to collect the electrons which are emitted from this plate. The outer part of the whole tube is blackened, and only a small window allows the light to fall on the plate C. The plate C, which we call as a cathode, is connected to the negative terminal, and the plate A is connected to the positive terminal. In order to find out whether the electrons are emitted, and if they are emitted, how much are emitted, we have got an ammeter which measures the current which will go as soon as the electrons are incident on the plate A. We have a potential difference because of the plates being connected to a cell, and that is measured by a voltmeter placed over here. Now notice carefully that this arrangement can also be used to reverse the voltage, that is C could be made positive and A could be made negative. We will see what happens when we do that. Okay. Moving forward, we see that whenever we have a particular way of light, for all possible lights of all possible frequency, we notice that the photocurrent is indicated by the emitter, or in other words, electrons are emitted by the plate C only when the light has a frequency greater than a fixed frequency, which we will call as threshold frequency. And now once we have this electrons being emitted, on increasing the voltage, we see that the current increases, but that it soon plateaus out or becomes constant. This value of constant current is called saturated current, and that depends upon the intensity. So if you increase the intensity, you will notice that the saturation current namely also increases. Next, if you reverse the potential difference, that is, now we are making C positive and A negative, that means we have got cathode, which was cathode is now becomes anode, and what was anode now becomes cathode. What will it do? Now it will stop the electron, or rather try to stop the electron from reaching A. So consequently the ammeter will indicate that the current is falling through, it is decreasing, as can be seen by the graph. Even at when you make the voltage 0, there is some current that is shown in the ammeter, but as soon as we decrease the voltage, the current goes on decreasing, and for a fixed value of negative potential, all current stops, and that is irrespective of your intensity. So if it has intensity E1, E2 or E3, all these currents stop whenever you apply a fixed negative potential to the two electrodes, and that is called the stopping potential. We go to the next thing and see that now what we do is we are ready to experiment with something more. We take light of different frequencies. So we have taken frequency V1, V2, V3, or rather mu1, mu2, mu3, mu1 being the least and mu3 being the largest. What we notice is when we use mu1, we have a certain value of stopping potential. The moment we increase the frequency to mu2, the stopping potential also increases. That means the stopping potential is directly proportional to the frequency of light that is incident on the plate. So if you draw a graph of different stopping potential for different frequencies for a given metal, we say that they are linearly related, that is, it's a straight line, and this line cuts the x axis or the frequency axis at the threshold frequency. Now we'll like to summarize whatever we have learned, okay, and we call them as laws of photoelectric emission. So first is, for a given photosensitive material and given frequency of incident radiation, of course above the threshold frequency for the given metal, the photoelectric current is directly proportional to the intensity of light. So once you get electrons emitted for a certain light, then the current is directly proportional to the intensity of light. The saturation current is directly proportional to the incident light. Second, for a given photosensitive material, there exists a certain minimum cutoff frequency below which no photoelectrons are emitted, however high is the intensity of incident radiation. This frequency is called threshold frequency. Above the threshold frequency, the stopping potential, or equivalently the maximum kinetic energy of the emitted photoelectrons, is directly proportional to the frequency of incident radiation, but is independent of intensity. The photoelectric emission is an instantaneous process. That means the light falls and electrons are emitted. Light falls, electrons are emitted. There is no time gap or time lag. Even if it is there, it is very small. So the time lag between incidence of light radiation and the emission of photoelectrons is very small, say around 10 raised to minus 9 seconds. Now this completely contradicts with the theory of wave theory of light, which we have learnt before we did this photoelectric effect. With wave theory of light, we could nicely explain interference of light, diffraction of light, polarization of light. Now we'll see what is the possible contradiction between wave theory of light and photoelectric effect. Firstly, light is an electromagnetic wave and it consists of electrical and magnetic fields. Now most important, they are continuous distribution of energy. That means they have a continuous distribution of energy from a lower value to a higher value across the region where the wave is extended. This wave picture of light could not explain the basic features of light we just discussed above. We shall list these basic differences now. So according to wave theory, when a wavefront of light strikes a metal surface, the free electrons at the surface absorb the radiation energy continuously, because the energy of an electromagnetic wave is continuous. It is not quantized, or it is not in fixed lumps, but it is continuous. Greater the intensity of light radiation, that means greater the amplitude of electrical and magnetic fields, greater is the energy density of the wave, that is the energy per unit volume of the wave. Hence, higher the intensity should liberate photoelectrons with greater kinetic energy. I repeat, higher the intensity, more and more electrons, or you should emit electrons with greater energy. Now this is exactly contrary to the experimental results we saw, namely that the maximum kinetic energy of the electron does not depend upon the intensity of incident radiation, rather it depends on the frequency. No matter what the frequency of incident radiation, a light wave of sufficient intensity should be able to impart enough energy required to eject the electron from the metal surface. This is as per wave theory of light. But according to photoelectric effect, this doesn't happen. That means more the light, the more the likelihood of an electron coming out. This doesn't happen. Here for wave theory of light, we need light of frequency greater than threshold frequency. Thus the wave theory fails to explain the very concept of threshold frequency. Now the energy of light wave is smooth and evenly distributed across advancing wavefronts. Each electron intercepts an insignificantly small amount of this energy. So it should acquire a finite time, or it should require a finite time to absorb all the energy required for it to come out of the metal. So here what happens, if when an electron meets light, it will slowly absorb the energy as the light goes on falling on it, and when it has acquired the amount of energy needed for it to come out of the metal, it will come out. So it won't be an instantaneous process as we saw in the case of photoelectric effect. Now all these contradictions that existed, Einstein gave a suitable explanation for this. In 1905, Einstein explained photoelectric effect on the basis of Planck's quantum theory, according to which a light radiation travels in the form of discrete photons. According to which light radiation travels in the form of discrete photons. Discrete photons. Photons are actually can be visualized as packets of energy. Each photon has a fixed amount of energy, and light of a particular frequency, all photons of light of a particular frequency will have the same energy. The energy of each photon is directly proportional to frequency, or you can see it, call it as h mu, where h is Planck's constant and mu is the frequency of light. The main points that Einstein's theory of photoelectric effects are: photoelectric emission is a result of interaction between two particles, one a photon of incident radiation and other an electron of photosensitive metal. Secondly, the free electrons are bound within the metal due to restraining force of the surface. The minimum energy required to liberate an electron from the metal surface is called work function of the metal. Third, each photon interacts with one electron. Now this is very important. Each photon interacts with one electron. The energy h mu of the incident photon is used in two parts. A part of the energy of the photon is used to liberate the electron or give the required work function W0. The remaining energy imparts kinetic energy to the electrons. So firstly, one photon interacts with one electron. The photon transmits all its energy h mu to the electron. This energy is used by the electron firstly to come out of the metal or do the work required to come out of the metal, and the balance energy is manifested itself as the kinetic energy of the electron. So very few photons whose energies are greater than W0 are capable of ejecting electrons by conservation of energy. Energy of a photon is equal to maximum kinetic energy of the photon plus the work function. So which we put it arithmetically as h mu, energy of photon, half m v max square, that is the maximum kinetic energy of an electron which is ejected, plus the work function. Doing a little bit of arithmetic, we can say that the maximum kinetic energy will be equal to the difference between the energy of the photon and the work function. Having noted that, we will go down to the next part. In order to explain the effect of intensity that we see, we say that the increase of intensity means the increase in the number of photons striking the metal surface per unit time. As each photon ejects only one electron, so number of ejected photoelectrons increases with the increase in the intensity of incident radiation. That means if the intensity increases, number of photon increases. Number of photon increases means number of electrons that it strikes will increase. Now we come down to explanation of threshold frequency. Now let us say that our frequency is less than mu0, the threshold frequency. The frequency of incident radiation is less than the threshold frequency. Now if you put this value in the equation which we studied, that maximum kinetic energy is equal to energy of the photon minus energy of work function. Now your energy of photon is less than energy of what? Energy of work function. So the kinetic energy will be negative, which is a contradiction, which has no physical meaning. So photoelectrical emission cannot occur the moment your frequency falls less than the threshold frequency. Now explanation of kinetic energy depending upon the frequency. Now we just said that the maximum kinetic energy is given by half m v max square, and that is directly proportional to the frequency. Above the threshold frequency, the maximum kinetic energy of electrons increases linearly with the frequency of incident radiation. Moreover, the increase in intensity increases only the number of incident photons and not their energy. So intensity only increases the number of photon, it does not increase the energy of the photon. Hence maximum kinetic energy of the photon is independent of the incident intensity of incident radiation. Now most important issue is the time lag. Photoelectric emission is the result of an elastic collision between photon and electron. This will explain everything. Photoelectric emission is the result of an elastic collision between photon and electron. Thus the absorption of energy from a photon to a free electron inside the metal is a single event. It's not a continuous thing, it's a single one event. Photon strikes electron, electron absorbs all the energy of the photon, that's it, finished. Which involves transfer of energy in one lump sum instead of continuous absorption of energy as in the case of wave theory. Hence there is no time lag between incidence of photon and the emission of electron. With this we come to the final conclusion that particle nature of light, that means we say light happens as a continuous stream of particles. Rather than particles we can call them as energy packets, and these particles are called as photons. So when light interacts with matter, it behaves as if it is made up of discrete packets of energy called as quanta. So a singular packet is called quanta, and a plural form of that is quantum. So each quantum of light has energy equal to h mu, and momentum is h mu by c. Notice h mu by c is the momentum. So the particle has energy and momentum, and the point that it has momentum tells us that it is a particle. The fact that a light quantum has definite energy as well as momentum allows us to associate a particle with it. Now the particle nature of electromagnetic radiation was further confirmed in 1924 by an experiment of A. H. Crompton on the scattering of X-rays by electrons. So when X-rays, which were primarily electromagnetic waves, if they can be scattered by electrons, we had a justification for the particle nature of electromagnetic radiation. The phenomena of increase in wavelength of X-ray photons scattered by striking an electron is called Compton's effect. In 1921, Einstein was awarded the Nobel Prize in Physics for his contribution to theoretical physics and photoelectric effect. Now let's look at some basic features of photon and its picture of electromagnetic radiation. Remember, in the interaction of radiation with matter, so whenever radiation interacts with matter, radiation behaves as if it is made up of particles, which henceforth we call as photons. Each photon has an energy equal to h mu, and its momentum is given by h mu by c, or rather h by lambda, where c is the velocity of light in vacuum. All photons of light of a particular frequency or wavelength will have the same energy independent of the intensity of radiation. Photons are electrically neutral and are not deflected by electrical or magnetic field. In a photon particle or a particle electron collision, the total energy and total momentum are conserved. So in that interaction between a particle and photon, or a photon and electron, total energy and total momentum are conserved. However, the number of photons may not be conserved. This is a very important point. The number of photons may become less or more. A photon may be absorbed or a photon may be created. So, number of photons are not conserved. If the intensity of light of a given wavelength is increased, there is an increase in the number of photons incident on a given area in a given time. So, intensity basically means more photons, more intensity, more photons, more intensity, more photons. But the energy of each photon depends on frequency, that remains the same. The frequency of a photon does not change as it travels from one medium to another, that we know that light's frequency does not change when it goes. The speed of a photon may change as it travels from one medium to another. The next interesting part is the photon cannot be at rest. If it is rest, it doesn't have mass, its rest mass is 0. So, a photon cannot exist at rest. For a photon whose velocity is nearly the velocity of light, not exactly same but near about, its mass will be equal to m into root 1 minus v square upon c square. So, the mass actually depends upon its velocity. So, as soon as it starts moving with the velocity of light, it will become 0. From energy mass conversion of Einstein, we know that E is equal to h mc square, which recently we studied, is equal to h mu. We get the mass of the photon as h mu by c square. But remember, this is all when it is neither at rest nor it is moving at the speed of light. Within that thing, you can say that mass of a photon can be described by h mu by c square. Consequently, its photon can be written as mass of the thing into velocity, so it will be equal to h by lambda. Now, we do a small experiment to find out Planck's constant and the work function. The idea is very simple. We just borrow something from Einstein's equation. You can say that K max is equal to h mu by work function W0. Let us say that mu 0 is the stopping potential. So, our K max will be equal to E mu 0. So, E into V0, V0 is the stopping potential. So, it will stop only when the kinetic energy is equal to the energy acquired by the electron on moving across a potential V0. So, we now write the value of E V0 instead of K max. So, E V0 will be equal to h mu minus W0. Divide both sides by E and we get this equation. Now, we will notice that this is very similar to something which we wrote, y is equal to mx plus c. So, if you look carefully, you will notice that this can be very similar to E is equal to mc by E is equal to mx plus c. So, m will be equal to h by mu and c will be equal to work function upon E. So, we look at the graph here. Yeah, so this is the thing. We have plotted stopping potential across the y axis and the frequency along the x axis. So, the graph indicates a linear line which cuts the x axis or the frequency axis. At that point, we get what is called as the threshold frequency. The slope of the graph gives us the ratio of h by E, and the y intercept which gives us c, which is minus work function upon E. So, if you plot the graph, you can calculate the threshold frequency, you can calculate h or E, you can also calculate the work function. E is a constant for electron, 1.6 into 10 raised to minus 19. So, this is how R. A. Millikan precisely determined the value of h and the work function for sodium. These values agreed well with the values known from other experiments. This led to the acceptance of Einstein's particle or photon picture of electromagnetic radiation. R. A. Millikan was awarded Nobel Prize in 1923 for his work on the determination of E and photoelectric effect. So, we come to the end of this section. The later part, when we look at particle nature, the wave nature of a particle and de Broglie's hypothesis in the next part. We will also see a few sums to reinforce whatever we have learned today. So we have come to the end of the session. Till we meet again for another interesting session, wishing you goodbye and thanks once again for coming and being with me. Thank you.